All right. Okay, this is lesson 10, inverse functions. Okay, so we've been talking about functions a lot. Now let's talk about their inverses, okay? What they are and all of that. So let's go back to functions in general. Okay, remember a function takes is like a map that takes inputs to outputs, right? A domain to a range. So you might have, your domain here, right? Your inputs and your range here. Right, and your function f will take, draw that again, will take your inputs and connect them to an output. Okay, well, there are sometimes inverse functions. Notate it with a little, looks like an exponent of -1. So f with a little -1. That takes your, what was once your outputs, they become your inputs and they trace you back to your original domain. Okay, 3 connects back to C, 2 to B, and 1 to A. Okay, so basically the x's are now the y values, right? The y's are now the x's. Okay, there's a switching, there's a backtracking. So you can think about it as your flight home, right? Okay, and so the notation for an inverse function looks like this, right? You have the superscript up here, which is a little -1. It's not an exponent, it just means the inverse. Don't think about that in terms of like reciprocal either, right? It's not the same thing as that. We'll do some examples to help reiterate that in a little bit, okay? So here's a pretty straightforward example. Here is a function, f of x is equal to 10x plus 8, and I want to find its inverse, right? That's what this is saying here, find its inverse. All right, and so to do that, this is a method that I like to use. It's not complicated. We know that f of x essentially stands for y, right? It's our y value. We could say that. It's more than that, but you could go ahead and replace the x and the y because that's what it gives you, right? The function value is a y value in your normal xy plane. And so if you're trying to find the inverse, you are inverting, right? Inverting your x's and your y's. Okay. What was once your y values is now going to be your x values. And what was once your x values will now become your y values. Okay, and so now I just want the formula, right? I want an expression that if I plug in a number for x, it'll give me this new y, right? Plug into the new x, you get the new y. So I need to solve for y. Okay, and that's pretty straightforward. I just subtract 8 from both sides. And then I divide both sides by 10. And so I have this x minus 8 over 10 equals y. That's the new y, right? So that means that my function, my inverse function, is x minus 8 all divided by 10. There's my inverse function. Okay, and so we can test it out to see does this actually work like it's supposed to. We can plug in some numbers. Let's say we maybe plugged in into f of x, we plugged in, say, 0. That'll illustrate the point. So what would my output be if I plugged in 0 for x? 10 minus 0 is just 0, so 0 plus 8 is 8. So that's the point 0, 8, right? X is 0, y is 8. Let's say I want to start with that 8, that given y value, and I want to trace it back. What would the x value be for the y value 8? Well, I'll just plug that into my inverse function. 8 minus 8 is 0. That's 0 over 10, which would be 0. Okay, and so notice it brought me back to my original whatever I plugged in. Okay, it's just a return journey home, essentially. Okay, and so here are the graphs of the two equations here. Okay, so f of x is 10x plus 8. That's, of course, this graph right here. So it's a a very steep line, right? And then we have this one right here, which is the graph of the inverse function. Okay, and you might notice, we talked about symmetry last week. You might notice there is some symmetry. Here are both of them on the same graph. Okay, the function itself is in red, and the inverse function is in blue. If you look at it, you can actually see that there's symmetry with respect to the origin, right? So that's what this dashed line right down the center is for. Okay, you can see that for every point here, there's a mirror point here. For every point here, which is, what is that? Almost, well, it's about -1/2 and then up 3. And then there's one down 1/2, 1, 2, 3. Oh, that's not it. 3. Okay, so there's a mirror point everywhere. And of course, where one graph touches the line in the middle, of course, the other one's going to touch as well. Right? It's like when you get to a mirror and you touch the mirror, the image and your actual hand, right? They meet up. Okay, so you can see the symmetry there. Inverse functions will have symmetry with the origin. And well, the original function and the inverse function will have symmetry. Okay, let's go and try this one here. Here we have our quadratic, our base quadratic here, x squared. So to find its inverse, we're going to go and say, all right, y equals x squared. X equals y squared. To get y by itself, I'll use the square root property. So that means that the square root of x is equal to y, but also negative the square root of x is equal to y, right? That's what the square root property says. If you have something squared equals something, then if you do the square root of both sides, essentially, that'll work, but you get a positive and a negative version. Okay, and so with that in mind, we have two formulas for y. All right, think about back to the definition of a function. This does not count as a function. So f inverse of x is not an inverse function. Okay, but we do have a formula for it. Okay, we have the square root of x, and we have negative the square root of x. I'll just leave it as y. I don't want to use a function notation. Okay, and so those will work, sorta. Okay, if you look at the graph, let me make sure I don't have the graph. Oh, yeah, that I do. Okay, you look at the graph of f of x, of course, here's your parabola. Here's a sideways parabola, right? It's still a parabola, but there you go, it's on its side. That would be the inverse. You can see the symmetry. Okay, this piece that goes up right here has a mirror image right here. This piece that goes up to the left has a mirror image that goes down to the right. Okay, those are mirror images here. That's our symmetry. Okay, so there's still symmetry even though this is not a function. And remember, it's not a function. You may remember the vertical line test from high school, right? In other words, there's an x value here. Here's when x is 3, where you have two different y values. And of course, you're going to have two different y values. Remember, there were two instances, a positive version of it and a negative version of it. All right, so that's inverse functions and some stuff about that. Let's talk about one of the criteria for having an inverse function is the function, the original function needs to be 1-to-1. Okay, so let's talk about that. Only 1-to-1 functions have inverse functions. They may have an inverse, but not necessarily an inverse function. Okay, and a function is called 1-to-1 if each y value is used exactly one time. Okay, and so let's look back at this example here. Each x value or each y value is used only once. That's not true for this, right? If I look at this function right here, I see that y value used twice. Here, y value is used twice. Okay, so if you're having a situation where the y value is being used more than once, it does not have an inverse function. It may have an inverse, but not an inverse function. And that's what we see here, right? This is not an inverse function. Okay, and so that's one way to look at it. This is the way we're going to use mostly though. A function is one-to-one if f of a equals f of b implies that a equals b. Okay, there's a lot more that kind of goes into that that I left out here. This is just the basics to help you understand what to do to determine if something is one-to-one. This is what you're going to be, this is what you're going to be checking. If I start with the assumption that f of a equals f of b, and like literally, I can plug in a and b, I should get at the end the only result that a equals b. That a equals b. That should be the only result that I get. Okay, so what does that look like? All right, well, let's go back to this example here. F of x is equal to 10x plus 8. All right, so I want to check to see if it's one-to-one. I'm going to start off with my base assumption that f of a is equal to f of b. I'm going to start with this assumption and I'm going to work it out. If I get a equals b as my conclusion, then I can assume that my original assumption was correct. If I get anything other than this, if I get a does not equal b, or a equals b and something else, then I would say that's a contradiction in the definition. So the original assumption was false. Okay, let's work it out. F of a equals f of b. All right, what does f of a look like? That means plug in a for x in the 10x plus 8. On the right side, f of b, I'm going to plug in b for x. So the left side is 10a plus 8. The right side is 10b plus 8. Now, if you solve for a or just trying to simplify it, you notice you have plus 8 on both sides. So I can subtract 8 from both sides. That will eliminate that. Okay, 10a equals 10b. And so I'm going to divide both sides by 10. And there's my conclusion. If f of a equals f of b, then a equals b. It followed from this original assumption that this would have to be the conclusion. So we would say that this one is 1-to-1. And we kind of already knew that. Remember, we knew it was 1-to-1 because we knew it had an inverse function. We had found it earlier. Okay, sometimes you'll see 1-to-1 notated like this, by the way. That means 1-to-1. Okay, let's go and try this one here. Okay, so I'm going to show that this one is not. We're going to start off with the same assumption. F of a equals f of b. All right, now let's plug that in. A squared on the left, b squared on the right. Oh, here comes that zero, the square root property. Here comes the square root property. If I find this, then I find that a is equal to positive and negative the square root of b squared. All right, so that and that's going to cancel, of course. So let me just jump to the conclusion here. A equals both positive and negative b. All right, that is not a equals b, right? That's very different. A could be two different things, a positive and a negative b. So we would say that this one is not 1-to-1 because we did not get a equals b. Okay, a few more questions, and these actually are going to come from Alex. Okay, so and you'll see this is not too bad, but it's a good idea to look at this question and really think about what it's saying. So the 1-to-1 functions g and h are defined as follows. Okay, so these are two 1-to-1 functions. Okay, it says find the inverse of g. Okay, so we're ignoring that bottom one for now. We're focusing on the top one. So g inverse of 4 equals what? Now, remember, g of 4 would be, okay, find the x value 4. Okay, that would equal -2. But you need to think about this in reverse. This is saying your y value is 4. What's the x value? Your y value is 4. What's the x value? Okay, well, here's my y value of 4. There's my x value, -3. All right, so it's really a reverse, right? A reverse of what you're used to. Okay, let's find the inverse of 5x plus 7. Okay, that's not hard. Y equals 5x plus 7. invert the x and the y. X minus 7 equals 5y. X minus 7 over 5 is equal to y. Therefore, we could say that the inverse is x minus 7 over 5. Okay, so same question. This time it says find the composition of h inverse of 2. Okay, well, first of all, h inverse of 2 would be 2 minus 7 over 5. Negative 5 over 5. That's negative 1. Okay, so 2 plugged into h inverse is negative 1. Now let's plug that output into h, right? So plugged there. Now we're going to go here. 5 times negative 1 plus 7. Negative 5 plus 7 equals 2. Hey, look, it brought me back, right? Okay, think about this. I did way too much work on this problem. Okay, the reason being, this input right here had to pass through an inverse and its function. The thing about an inverse function is its entire purpose, essentially, is to cancel out the other function. Okay, so an inverse composed with its, a function composed with its inverse cancels each other out to leave you with the original input. Okay, that's what's happening here. All right, here's another question that you might see on ALEKS. The one-to-one function of g is defined below. So here it is. Find the inverse of g, where g is the inverse. Yeah, okay. So we're going to find the inverse of g. All right, y equals 4x minus 5 over x plus 2. I'm going to go ahead and skip this part and put my y's in now and my x here. All right, I want to get rid of the denominator, so I'm going to multiply both sides by y plus 2. All right, so the y plus 2's will cancel out on the right side to leave me with 4y minus 5. Left side, I have x times y plus 2. I'll distribute the x. Okay, now I want to get all the y's on the same side, so I'm going to subtract 4y from both sides. Just going to move this up here. So subtract 4y from both sides, xy minus 4y. I will also subtract 2x from both sides. So give me a negative 2x on the right side, minus 5. Okay, then I'll factor out a y. And divide both sides by x minus 4. That is my inverse. Okay, and the last thing we need to talk about pretty quickly is to find the domain and the range of this inverse function. Okay, the domain and the range of this inverse function. Okay, well, what we first should do is find the domain of the original, this 4x minus 5 over x plus 2. All right, my domain is going to be everything except for the x values that makes the denominator 0. And so in this case, that'd be negative 2. So the domain for g of x would be negative infinity to negative 2 to positive infinity. Just no -2 involved. And that's the domain. Okay, and so the range would be -infinity to 4 to positive infinity. All right, so then the domain of the inverse and the range of the inverse, since you're switching out your x's and your y's, are just going to be these in reverse, right? So the domain will be, and I'll put it in interval notation this time, -infinity to 4 union 4 to infinity, right? Which is the range of G. And the range of the inverse would be the domain of G, -infinity to -2 union -2 to infinity. Okay, so that would be inverse functions, their domains and ranges.